Welcome! Today we will talk about the substitution rule. The substitution rule is a nice way of reversing the chain rule. So given something very complicated, I can turn it into a simpler expression, then anti-differentiate that simpler expression and re-express in terms of x. Let's see how this works. So recall the chain rule. Let me do a few quick chain rule problems using derivatives. So the derivative of sine of 4x squared, I take the derivative of the outside, leave the inside unchanged, and then multiply times the derivative of the inside. How about 3 times e to the sine x? Well, constant multiple, so this so the 3 stays there. The derivative of e to the x is e to the x, so I take the derivative of e, the inside stays unchanged, and then multiply times the derivative of the inside, so it becomes cosine in that case. Now here I have a 1/10, so that when the 10 comes out front, that'll just give me 1. And I have a bunch of stuff to the 9th. The inside stays unchanged. 1 over x plus the square root of x. And now I multiply times the derivative of the inside, negative 1 over x squared plus 1 over twice the square root of x. How about logs? Do you remember the derivative of a natural log? So it's 1 over the argument, 3x to the 4 minus 10, times the derivative of that thing. So maybe in the numerator, I'll just put 12x cubed. And lastly, here it is in its abstract generality, the derivative of f of g of x. I take the derivative of the outside, f prime, leave the inside unchanged, and then multiply times the derivative of the inside. All right. So at this point, let's think about reversing this process. Our challenge is to reverse the chain rule. Suppose that we are given indefinite integral problems. These look kind of messy. But if these were the types of problems that were given to us, and we didn't know the original functions where they came from, how could we recover the original function that I took the derivative of? And that's what substitution is all about. It's a step-by-step process for helping us figure out these antiderivatives. All right, so I'll show the general method on the left, and I'll do a specific example on the right. Let's suppose I have an expression of the form the antiderivative of f prime g of x times g prime of x dx. It's the result of the chain rule. And on the right, I have a very specific example. Take this antiderivative. So our first step is to identify the inside function. What is inside the f prime? So I can literally see it on the left, inside the parentheses. On the right, it looks like inside of the cosine. And I'm going to give that a new, simpler name. I just call it u. So let u be that function on the inside. So on the left, let u be g of x. Then I can figure out du dx. That's just my g expression. Take the derivative of that. So on the right, du dx is just 8x. And next I do something a little bit funny. Let's treat that du dx like it was a fraction. And if it was a fraction, this dx on the bottom could be multiplied by both sides. And I can solve for du. So du is g prime of x dx. On the right, du is 8x dx. So now at this point, I can do substitution. And what will I substitute? Look what I have here on the left. I've assigned a value for u as g of x, and so I can substitute in a u in that place. Also, du is a g prime of x dx, and I see g prime of x dx, so I'll replace that with du. So on the left, it's pretty straightforward what I get. But how does this work on the right? On the right-hand side, the inside, the 4x, well, that was pretty easy. That just got replaced by u. But now I need to find an 8x dx, and I'm left with a little bit of a question mark. I don't really see an 8x dx, so what am I to do? Here's a trick. That x that's in front, I want to see it being an 8x, so let's multiply by 8 and also multiply by 1/8. And so I'm not changing the problem. I'm multiplying by 8 and dividing by 8, but I'm changing how it looks so I can see I have an 8x there. Also, I have my dx, and even though they're separated, I can think of this whole thing like sort of like a multiplication of 3 items, 8x, cosine u, and dx. The 8x is what comes out and gets replaced with a du. So I can take the 1/8 constant and bring it out front. It's a constant multiple. 1/8 comes out front. The 8x dx gets replaced with a du, and I'm left with 1/8 cosine of u du. So see how I've simplified the problem. The original problem that I started off with was a little bit more complicated than this problem that I've got right now. So what do I do now? Anti-differentiate. So far, I haven't done any antiderivatives. I still have the integral sign in there. So now is the time when I finally find the antiderivative. So on the left, we can see the antiderivative of f prime of u, du, is f of u plus c. I should really be saying indefinite integral instead of antiderivative. So the indefinite integral is all those antiderivatives. And similarly on the right, this cosine u will become sine of u, and I stick a plus c on there. Now I'm not done yet. I have one last step, and that is to replace the u with what it really represents. U was really g of x, so I can put that back. And on the right, u is really 4x squared, so I get my answer. All right, let's do some more examples, see how this works. So the first thing I want to do is look for an inside function. I see a big square root, and there's an expression inside that square root, so that's a good candidate for my u. So let u equal x squared plus x. Then du dx is 2x plus 1, and so du equals 2x plus 1 dx. After this point, I'm going to skip that middle step, and I'll just go directly from figuring out u to figuring out du. But now I'm ready to substitute. So for the u part, that's pretty easy. I have a square root of u in there. But there are some other things floating around. I still have that 6x plus 3, and I have the dx to worry about. I'd like to see a 2x plus 1 dx. I don't quite see that, do I? Well, maybe. How about this guy on the left? This 6x plus 3 is really the same thing as 3 times 2x plus 1. And there it is. So I want to see 2x plus 1 dx. I have my 2x plus 1 dx there. So I'm left with a 3, and then the 2x plus 1 dx, all that gets replaced with a du. I get a du. So let's anti-differentiate that guy. So 3, well, let's see here. 3 can come out before I anti-differentiate. Let me just write this as u to the 1/2 du. Now I can anti-differentiate. And 3, see, I need to raise the exponent by 1. So that's 3/2. And then multiply in front by the reciprocal of that new exponent. You'll see I often leave a little space between the constant multiple and the function if I think I'm going to have to introduce a new factor. And this is plus c. So as our last step, let's see, I'll simplify that, and I'll replace the u with what it really represents, and the u is really x squared plus x. There it is. Another example. Let's see, I need to identify the inside function. I see a square root, I see stuff inside the square root, so that's a good candidate. Let's try that. U equals x to the 4 plus 1. Du equals 4x cubed dx. Let's substitute. So in the denominator, that'll just be square root of u. How about my numerator? I see 8x cubed, but I'd really like to see 4x cubed. I guess that's really like 2 times 4x cubed dx. So I can take that 4x cubed dx and replace that with the du. So I get the integral of 2 over square root of u du. And again, I'll simplify a little bit. How about 2 times u to the negative 1/2 du? All right, I think I'm at a point now where I can anti-differentiate. Constant stays there, leave a little space. U, raise the exponent by 1, so I get a positive 1/2. Multiply in front by its reciprocal. Add c. And now I think I'm ready. Let's see, what is the u? The u was x to the 4 plus 1. And that's raised to the 1/2 power plus c, and I'm done. All right, another example. This one, it's not entirely clear what my u should be. I don't really see an inside function. But I do see something that's suspicious. This top, the numerator, 5x to the 4, is almost like the derivative of the bottom. The derivative of the bottom is 15x to the 4. So I'm just off by a constant factor. As a general rule, if you don't see anything that kind of really pops out at you as being your inside function, try the denominator of the fraction. That's often a good choice. Let's see what happens when we do that. U equals 3x to the 5 plus 10. So du is 15x to the 4 dx. Now, when I substitute, that whole denominator just becomes u. Now, I'd like to see 15x to the 4. Instead, I see 5x to the 4. How can I massage that a little bit to turn it into what I want to see? If I multiply by 3, that would work. So I need to put a 1/3 times 15x to the 4 dx. There we go. So the 1/3 and the 15 are going to multiply to give me the 5, like I have originally, but now I really see it as that expression that gets substituted out for the du. All right, so I'll put the 1/3 out there, and all I'm left with is 1 over u du. Oh, well, how do I do this? Do you remember? What is the indefinite integral for 1 over u? It's the natural log, and we do need to use absolute value. When you do these problems online, the computer really wants to see absolute value. Almost done. Last step is to substitute the u's out for what they were originally in terms of x. U is 3x to the 5 plus 10. 3x to the 5 plus 10. Don't forget your constant of integration c, and you're good. All right, last example. Compute the indefinite integral of 1 over x squared dx. Maybe pause the video for a second if you think you know how to solve this, and then unpause when you're ready to take a look at the answer. Okay, assuming you've given it your best shot, here's the answer. All right, I'm sorry, it was a trick problem. Did you get that? Did you see? You don't have to do any kind of substitution for this problem. This really is just the tan inverse of x. Okay, but here is a better problem. Here's the real example 5. How about this one? 5x to the 4 over 1 plus x to the 10 dx. I told you before that if there's nothing obviously that works as an inside function, go for the whole denominator. But here's a situation where you don't want the whole denominator as your inside function, as u. Based on what's at the top, do you have a choice? Can you see what u should be? Let me rewrite this problem. 5x to the 4 all over 1 plus x to the 5 squared. Now do you see it? I can really let u be x to the 5. Then du is 5 x to the 4 dx. So I'm in a nice situation where the u, x to the 5, is clearly given. And also the du, 5x to the 4 dx, is exactly what I see up above. So upon substitution, this whole integral becomes 1 over 1 plus u squared du, which is exactly my tan inverse. So now when I anti-differentiate, this becomes tan inverse of u plus the c, and then substituting back the x's, tan inverse of x to the 5 plus a c, and that's it. All right, give these homework problems a try, start getting a feeling for substitution, and we will do a little bit more in our next lesson.